Thank you for introduction. Okay. Today I will talk about ABCI and its communication performance. So this is the outline of today's talk. So first, let me introduce the AIST, our research institute, and the ABCI, our system. And then I'll explain the detail about ABCI. And then I will show some embedded performance on ABCI. And finally, I show the latest application performance on ABCI. And AIST is one of the national research laboratory in Japan. It's a part of the Ministry of Economy and Trade and Industry. And so basically, we conduct applied research, so not basic research. So our mission is to integrate scientific and engineering knowledge to address industry and society needs in Japan, and then bridge the gap between innovative technological seeds and commercialization. So, this figure shows the current our vision, and these circles are research division in our research center. So currently there are 7 research divisions. For example, energy and environment, and material and chemistry. And I and my team belongs to this information technology and human factor division. And our mission is to popularize AI technology and robotics technology in Japan to build a sustainable society. So that's why we build and operating ABCI. And this is a brief overview of the ABCI. Again, so ABCI stands for AI Bridging Cloud Infrastructure. And this butterfly is a logo of ABCI. And this logo and the name includes our message that we'd like to spread and popularize AI technology in Japanese society and industry. And, so ABCI is the world's first large-scale open AI infrastructure, and it's located near from Tokyo, which is the capital city of Japan. And so its operations start from last August. So 1 year has been passed since the operation start. And the theoretical performance of ABCI is 550 petaflops in half precision, and 37 petaflops in double precision. And the effective performance as of June 19th, so ABCI is ranked in number 8 in top 500, number 3rd in Grade 500, and number 5th in HPCZ. And ABCI is a public and a dedicated infrastructure for AI and big data application. And our aim is to build open innovation platform to accelerate joint academia and industry research and development for AI. So actually there are many achievements in this first year operation, but I want to share some of 1 year achievement. So currently, there are more than 100 research projects and more than 1,000 users from academia and research institute and companies. And so basically, many of them are Japanese, but some of them are non-Japanese. And actually, so some member from TK's team has the ABCI account, and then to test and evaluate MVAPICH. And some large Japanese companies start to use ABCI as their R&D platform. And actually, so one of the large companies in Japan occupies almost 10% of whole ABCI resources. And as the perspective of the technologies, ABCI support NGC containers. So NGC is a NVIDIA GPU cloud, and NVIDIA publishes container images for CUDA development, AI, and HPC on the NGC container registry. And by using Singularity, so ABCI user can run containers using such NVIDIA's container images. And this is a blog article posted by NVIDIA this June. And as a research achievement, Sony and Fujitsu Lab achieved a good performance of ImageNet 1K classification on ABCI. So I show next slide. And finally, so 2 research papers that use ABCI were accepted by this year's SC conference. And I explain one of them at the last of my talk. And this is the world's fastest speeding ImageNet 1K training. This. And this is a timeline and record achiever. And the bars are relative speed up against the first one. And the orange lines are accuracy. And these green bars are conducted on ABCI. And last November, Sony achieved the best performance of the ImageNet on ABCI. But only after a few days, Google beats this record. But early this year, Sony again and Fujitsu also conducted the training on ABCI, and Fujitsu achieved the best performance at that time. And the latest result is published as part of the MLPath training. And so in this case, so at that time, so Fujitsu Lab further improved the performance. And you can find detail on this archive article. So I go deep into the ABCI. So this is the hardware overview of ABCI. ABCI consists of 1,088 computing nodes equipped with GPUs. Each node has 4 NVIDIA Tesla V100 GPUs and 2 Intel Xeon Gold CPU. And they have 384 gigabyte memory and 1.6 terabyte SSD and 2 InfiniBand EDR HCA. So the compute node is very similar to Summit, but it's very compact than Summit. And we also have 3 types of large-scale storage. So 2 are for POSIX file system and raster GPUs, and we also provide Amazon S3-like object storage. And they are connected by InfiniBand. So this is a software stack of ABCI. So actually, C in ABCI stands for cloud, but we use the software stack similar to a supercomputer. So that's why we use job scheduler. So for job scheduler, we use Unimagrid engine, so a so-called UGE. And we provide a container runtime, and 2 types of container runtime. So one is Docker, which is integrated in UGE. And the other is Singularity. And for MPI and development tools, so our basic idea is to provide building blocks for running various kind of AI workload, and at the same time to keep the system as simple as possible. So based on this idea, we provide many versions of MPI, including MVAPICH, and compilers, and CUDA, and GPU libraries. And users can easily select one of them and combine them to configure their own development environment. So this is a detail of ABCI's computing node. So again, this is a spec. And we use Fujitsu's server. And this is a picture of compute node. So the width of the compute node is half size. And this picture is the main board. So there are 2 CPUs and memories and HCAs, etc. here. And on top of it, this GPU board is located. And this is a block diagram of ABCI. So 2 GPUs are connected to CPUs through the PCI Express switch. and 4 GPUs are connected by NVLink. And so ABCI architecture is very symmetric, except for this SSD. So this symmetric architecture enables easily achieving high performance when multiple compute nodes are used. So this is ABCI's rack and interconnect architecture. So each rack has 34 compute nodes, and there are 32 racks. And so as a result, the peak performance of a rack is 1.16 petaflops in double precision and 70 petaflops in half precision. And so for interconnect, we adopt part tree topology. But so within a rack, we provide full bisection boundaries. However, so between rack and spine switch, the bandwidth of this link is narrow. So actually, so bandwidth of this link is the 1/3 of the aggregated bandwidth of the rack. And so we currently do not use adaptive routing and do not use Mellanox Sharp. This is a reason why I chose such interconnect design. So we choose 1/3 over subscription network because this is a cost-effective solution. And so before making this decision, we analyzed deep learning training workload on a GPU cluster dedicated for AI research. And so this is one of the analysis results on the GPU cluster. So this is a very small system compared to ABCI. So number of nodes is less than 40, but each node has 80 GPU. And so actually this is this was a pre-ABCI system. And so this graph shows the distribution of number of used GPUs and nodes in deep learning training jobs. This graph shows the ratio of single GPU jobs and multi-node jobs and single GPU job and single node job and multi-node jobs. And as can be seen from here, so single GPU jobs are dominant, so more than 90%. And this is a number of used nodes in multi-node jobs. So this figure shows the number, a degree of parallelism is very small. So from this observation, we designed ABCI for capacity computing system for AI. So go back to the previous slide. So again, so many deep learning actual deep learning workload do not use large number of nodes, and so high bandwidth network is required only a small subset of nodes. So that's why we adopt oversubscription network. And so second, the reason why we do not use adaptive routing is so when InfiniBand in ABCI is shared by a communication of computation and I/O. Yes.
Have you seen any issues when, for instance, like some deep learning application is reading some large data set, the compute performance or let's say the communication performance gets affected?
I haven't had such a situation, but so if users need high bandwidth I/O, so they usually copy data from the global storage to the local SSD. So at least currently we don't have such a problem now.
Do you plan to deploy quality of service using virtual lanes to isolate compute and I/O traffic?
Actually, so currently we don't have such plan. But if it benefits our users, we plan to consider such configuration.
Thank you.
And then so the reason why we don't use adaptive routing is so InfiniBand so again so and also the delivery provider Fujitsu suggested us not to use adaptive routing on such a network. But I'm not sure this is the correct decision or not. And so finally, we do not use Mellanox Sharp because so we use EDR HCA, and our switch do not support a large size reduction in Sharp, so it does not benefit our users. So from here, I show some performance result on ABCI. So first, I show you the performance impact on MVAPICH communication and 1/3 over subscription without adaptive routing network. So here we measured point-to-point host memory to host memory transfer performance. And we measured two scenarios. One is the interlock. So in this case, we split 34 nodes into two 70-node groups and increase the number of communicating nodes from 1 to 17. And the other is interlock communication pattern. And in this case, we randomly select 2 racks and then increase the number of node pairs from 1 to 34. And this is interlock P2P performance. And so this figure shows the per node average throughput and aggregated throughput. So as the interlock network is full bisection and logically non-blocking, so we can achieve more than 80% of the logical performance. And this is interlock performance. This result is just an example node pair selection, and so actual performance can be changed depending on the node pair selection. And so as you can see from these figures, there is a large performance drop as the number of connections is 6 and 20, and the actual performance is far from the ideal performance. So we think that this is caused by the static routing, and we now consider enabling adaptive routing. And so next is the collective communication performance on ABCI. So here we measure the performance of 2 collective communication. One is all-reduce, which is essential in distributed deep learning training. And the other is reduce, so which is the most heavy communication in our application. I explain later about the application. And these are the software configuration. And here I measure 2 scenarios. One is host memory to host memory transfer, and the other is GPU memory to GPU memory transfer. And host memory to host memory transfer, we use MVAPICH, IntelliMPI, and OpenMPI. And we use the previous version of MVAPICH. And in GPU to GPU case, we use the previous version of MVAPICH to GDR, and to compare performance, we use Nickel. This is a host memory to host memory all-reduce performance. So actually, so OpenMPI performance is not here the medium size message, but IntelliMPI and MVAPICH is very comparable. And at least in the in 2-rack case, the performance do not suffer from the 1/3 over subscription network. And this is a host memory to host memory reduction. So in this case, MVAPICH is apparently faster than others in the small size of message. However, if the message size is bigger than around 1 megabyte, IntelliMPI outperform others. So actually, so when the message size is around 64 megabytes, they are about 2 or 3 times higher than MVAPICH and much higher than OpenMPI. And this is a device memory to device memory or reduced performance. So this is a very complicated figure, but so except for at this point, it may be noise. So MVAPICH to GDR achieves the best performance when the message size is small. However, the message size becomes bigger. Nickel achieves a better performance. And this is device memory to device reduced performance. So in this case, so MVAPICH to GDR achieves the best performance. So finally, I want to introduce the latest ABCI application and its performance. So I show the iFDK, which is a high-speed and high-resolution CT image reconstruction framework running on GPU clusters. And so CT is compute tomography, and so iFDK stands for the instant FDK, and the FDK is a famous algorithm used in CT image reconstruction. And so what it does is just creating 3D images from the multiple 2D XA array images. And so this is a work between AIST and Tokyo Tech, and will be presented at this year's SC. So from Tokyo Tech, student Chin and Professor Matsuoka joined this project, and from AIST, Dr. Wahib and Takano and I joined this project. And so the main, there are three achievements in this work, but today I will talk about this only this one, because it is only this is related to MPI. So this is an outline of the distributed framework for high-resolution image reconstruction. So each CPU loads 2D images from the shared file system, and then conduct filtering operation, which is the pre-processing of the main computation on GPU. And after the filtering is done, we conduct the altogether between some number of node groups. And after communication is done, so as data copied to the GPU memory, and then back projection computation is conducted on GPU. And after that, the data is copied back to host memory, and then reduction is called to store the final output. And we use MPI for all reduce and all gather and reduce. But our current implementation do not use CUDA MPI. So MPI is conducted only on the host memory. And this is an example running scenario of the application. So in this case, we assume that there is a 4K count of 2K images, and the output size is 4K cube, and run on 32 compute nodes. In this case, we assign 128 GPUs. It was like discrete. So the number of column is 4, and the row is 32. And input image size is 16 megabyte in this case, and we split this number of images into 4 groups, which is the number of columns. And then we conduct all together in this group. And after all computation is done, we call a reduction in this direction. And as a result, the output 3D volume is divided into 64 sub-volumes, and each of which has 8 gigabytes. So actually, the reduction and altogether is very large size. So for together, each message size is 16 megabyte, and the reduction is 8 gigabyte. It's very big. And this is the performance of this scenario. And we compared Intel MPI and MPH2 and OpenMPI. And so as can be seen from here, Intel MPI is fastest. So this is because so the performance of altogether reduce is very different. And as a result, in the paper we use Intel MPI. But for the next step, to fill the performance gap, we plan to tune parameters for collectives and use CUDA and MPIs. And this is summary. We introduced ABCI and its communication performance and application example. And for future work, as a research, as a service provider and as a user of MPI, we plan to evaluate the latest version of MVAPICH and also continue catching up with MVAPICH. And we also provide detailed communication performance results of MPI and Nickel to our ABCI users. And that's all. Thank you.
Let's thank the speaker.